Hi guys, so in this video I'm going to talk about low latency and ultra low latency C++. So a lot of people have been demanding this video in the comment section. So basically I have finally decided to make it. So you might have heard these terms because a lot of high frequency trading firms and hedge funds and stock broking firms, they hire developers who are specialized in C++, who are specialized in creating low latency and ultra low latency applications. So what is an ultra low latency or low latency application? Like a program or an application is said to be low latency if its end-to-end latency is just a few microseconds, so like a single digit microsecond, and an ultra low latency application is one whose end-to-end latency is just a few nanoseconds. So what kind of optimizations we do to achieve such tight latencies? And like there have been few techniques which have been discovered by people in the past. So like some of those techniques are used, and people are like software developers or C++ developers, they are continuously researching, continuously optimizing their programs and discovering these new techniques. Like a lot of techniques you will find on CppCon as well, but yeah, I am going to discuss one such technique today. So let's understand the technique with the help of a question. So the question is simple. Like this question has been asked in a lot of trading companies interviews as well, a lot of HFT and hedge funds interviews, not just in India but in United States and Europe as well. So yeah, so question is simple, that you have to write a function to compute GCD of two numbers. GCD is basically greatest common divisor. In case you do not know what GCD is, you need to stop watching this video and watch some elementary math video. But anyways, like I hope you understand what GCD is. But the constraint is that the GCD function should return the result at compile time. Now again, it should return the result at compile time. It's not runtime, it's compile time. Now you might be wondering, oh, how a program can generate a result at compile time? Like compile time basically consists of compiling the source code and generating object files, linking a bunch of object files together and the library object files, and then finally creating an executable. And that executable has like machine instructions, like instructions which are read by the machine. And when that executable is run, that is the moment when your programs or your functions run and generate results. But how can we generate the result at compile time? Well, there is a way in C++ to do that, and you can understand the significance of this compile time. Like if your program is able to run at results at compile time, so it means that like the latency of it at runtime is almost zero, right? Because like everything is available at compile time. When you run that program, the result will be immediately available to you. No instructions have been generated for that program which like for that particular function which need to be executed, because the result was already available at compile time. So the latency is almost zero. So this is why like HFT firms ask these questions, because they also do these kind of optimizations in their day-to-day work, and that's what make their applications very fast. So anyways, let's understand it. So let's first understand how would we basically simply solve this question, like if this compile time constraint wasn't there. So the algorithm for GCD is very simple. Like GCD a comma b is equal to GCD of b a mod b, and GCD of a and 0 is basically a. So this is a function which I have implemented, a GCD function which takes two integers a and b, and if b is 0 it returns a, and otherwise it returns GCD of b comma a mod b. Okay, and let's run this function. So it would basically generate the output like GCD of 5 comma 15 is 5, 21 31 is 1, and 621 is 3. So this was a simple program. Like everyone know this particular algorithm. This is basically Euclidean algorithm, and everyone could have implemented, but this program won't generate the result at compile time. Okay, so let's see how we can generate the result at compile time. So basically it turns out that there are two concepts in C++ which you first need to understand. So one of the concept is, which was introduced in C++ 11 actually, which is Const Expert. That is Const Expert keyword, which basically stands for constant expressions. So so in C++ a variable or a function can be made Const Expert. So like you can understand Const Expert like this. Like you might already be aware about const. So if you write something like this, that const int a is equal to 5, so this means that a is a constant integer and its value cannot be changed throughout the program. Okay, so C++ introduced this Const Expert. So what Const Expert int a equal to 5 says, that a is a constant, a's value is fixed to be 5, it cannot be changed throughout the program. But it also says that the value of a will be initialized at compile time only. Okay, so that's what it means, constant expressions. Like the value of a will be available at compile time. With const, this wasn't guaranteed. And the other technique is templates in C++. Like I'm not going to explain templates, but templates in C++, like it is basically a way of writing type independent or type generic programs. You can read about templates in C++. And Other technique is template metaprogramming. Again, you can read about that as well. And using these three techniques, like these three techniques are widely used in all of the trading companies, and using these three techniques you can write like absolutely low latency software, because all these things are compile time things. Like templates are instantiated at compile time, so if you write your program smartly, then the results will be available at compile time as well. So let's look into the GCD program. So what I have basically done is that I have instead written a template for GCD. So this is a GCD template. So it is basically a struct GCD, okay, and it has only one variable, only one data member, which is value, and that data member, its type is, it has a static data member, and it is constant expression. It's basically Const Expert, and it is of type int. So it guarantees, since this is Const Expert, it guarantees this data member or this member variable is Const Expert, it guarantees that its value would be available at compile time. Now we need something with which we can initialize this value. So the way I am initializing this value is this, that if, so this template basically indicates GCD of a comma b, so this value will actually contain the GCD of a comma b, okay, and we know that from Euclidean algorithm that GCD a comma b is GCD b comma a mod b. So I'm initializing it with GCD b comma a mod b value, and then like as you might have noticed that in the recursive solution we had this base case that if b is 0 you return a. So there is a to actually code that base case in template metaprogramming or in the form of templates. Like we need a base case here as well. So the base case here is basically a partial specialization of the template. So this which I have written is basically called partial specialization of template. Like this was a simple template and this is partial specialization of template, and there is another concept called full specialization of template. Like you can read about these three things on Google. You might be aware about them as well if you have done some programming in C++. These are like very basic concepts. Anyways, so this is a partial specialization which takes one template argument int a, and it is specialized for a comma 0, and it says that, and it has the same data member value which is of static type and Const Expert. Again, you can read on Cpp reference or c++.com that what is a inline member variable. Okay, you might have seen inline member functions, but in C++, I'm not sure whether in C++ 11 or 14 or 17 the concept of inline member variables was also introduced. So this member is basically inline. So inline static Const Expert int value. So this value will contain the GCD of a comma 0, and that is, we know, is a only, right? So this is basically our base case. So what would happen when I would call this GCD, when I am calling the template with these arguments 5 comma 15? So what would happen that it would instantiate the corresponding structure from this struct template at compile time, okay, and recursively, since this value is initialized by this GCD b comma a mod b, so like recursively it will keep on instantiating other templates as well at compile time, and eventually this base case would be hit and the value will be initialized. For that base case the value would become a, and then like all the other templates will be initialized as well. So this is what I have done here. So when I will run this program, you can see that this will compile successfully. Like no result is printed because I am not printing anything. This static assert basically is a compile time check. It checks whether whatever you are static asserting is actually true at compile time or not. But let's take this case just to show you that it is actually computing the correct results at compile time. If, as we know that GCD of 5 comma 15 is not is equal to 5, okay, so if I will GCD of 5 comma 15 is not is equal to 15. Let's take this. So this should actually fail. The compilation should fail because GCD of 5 comma 15 is not 15. So when I run this, you will see that the compilation has failed and it is saying that static assert GCD 5 comma 15 is equal to 15 failed. So this guarantees that this program is actually running at compile time, right? So this is one of the you can say technique by which we write low latency C++. Like almost all of the trading companies use this template metaprogramming technique. I mean, everyone heavily uses templates whenever you are talking about low latency or ultra low latency softwares. And just to give you a feel as well, like what happens at compile time, so let me show you. So this is a website called Cpp Insights. So here it actually shows like whatever program which you have written, it shows what compiler generated for this, like what was the code generated by compiler for this. So you can see that I have just pasted the program which I had here on this website. So this is a template of GCD and this is a partial template of GCD. So you can see what happened at compile time is that all the templates, when I called GCD 5,15, all the other templates were instantiated. Like this is here you can see that this GCD 5,15 template was instantiated. This is a full specialization actually. As I mentioned, like there are like 3 types of things in templates. Like this was a template, this was a partial specialization, and this is a full specialization. And then from 5,15 this was generated 15,5. Then from 15,5 this 5,0 was generated, and you can see that value was initialized to be 5 here, right? So you can see that and here also you can see that GCD 5,15 the value is initialized to be GCD of 15,5, and then GCD of 15,5 the value is initialized to be GCD of 5,0 value, and GCD of 5,0 value is this. So you can see that all the code has been like the values has been generated at compile time only. And this is a partial specialization as well, which we had written. So, and you can say it also mentions that this static result actually passed at compile time. So I hope I'm not sure how much everyone understood this, but I just wanted to show you a technique by which we write low latency, ultra low latency C++ application. I just think that you might have got a feel for this, what we like what the trading companies do. And yeah, I think that was mostly it for this video. So if you guys think this is pretty interesting, then yeah, you should definitely make a career in HFT firms. But if you think that this is not at all interesting, this is pretty daunting, then maybe HFT is not the field for you. Anyways, thank you guys for watching. Please do not forget to like, subscribe and comment on this video, and I'll see you all next time.